Okay, hello everyone, and welcome to week 3 lecture slides. And we're going to go through the slides in 3 sections. So, this week we should cover the topics that listed here. First, we're going to have an introduction, tolerances, the fundamentals of tolerances, the functional dimensioning, and the tolerances. Then we're going to talk about the geometric dimensioning and tolerances, the fit, which include the tolerance, allowance, and the clearance, the geometric dimensioning and the tolerancing, the clearance fit, the interference fit, and the transition fit. Then we're going to talk about the dimensioning and the tolerances in the SolidWorks, which is going to be part of your practical session for this week. So in the first video, we're going to cover the introduction and the tolerance. So we start with the introduction. First, we're learning objective of this slide is going to be first, define the terms of the tolerance, allowance, the unilateral allowance, and the bilateral allowance. Also, we're going to describe the relationships among the tolerances, the production processes, and the cost. Also, specify the basic sizes for the dimensions according to the set of the preferred sizes. We're going to use the ANSI standard B4.1, preferred limits and fits for the cylindrical parts to specify the tolerances, fits, and the clearances. Continue with that, we are going to specify the transitional, interference, and force fits, specify the appropriate geometric dimensions and the tolerancing controls for the mating parts, specify the appropriate geometric dimensions and the tolerancing control for the mating parts using the CAD software SolidWorks. So first, let's have definition for the tolerancing and fit. So the ISO system of the limits and fits is coordinated system of the hole and the shaft tolerances for the engineering and the manufacturing use for the cutting tools, the material stock, gauge, and extra. So if held to these tolerances, the cutting tools, the material stocks, and the gauges are going to be generally available throughout the world. The hole basis fits have 4 preferred hole tolerances, which is going to be the H11, H9, H8, and S7. So you can see that for the hole tolerances, it's going to have mainly a capital letters. The shaft bases fits have a 4 preferred shaft tolerances, going to be the H11, H9, S7, and H6. Difference is we are going to use a small letter. So something like we're going to have shaft go inside the hole. So the hole is going to have the tolerances basis is going to be the fit basis is going to be the capital letter and with numbers, and for the shaft it was going to have the smaller diameter is going to be a small letter with a number. Usually it's going to have the H. The above shaft tolerances are covered in the ANSI B3200 for 2005 standard. By the way, the ANSI means the American National Society for Standard Institute. Sorry, the American National Standard Institute. Now we go once again to the example. We have a needle ruler bearing. So in the roller bearing, we are going to have the rollers, as you can see here. We call it needle because it's going to be a quiet small diameter, and this will roll with the shaft. So the shaft is rolling, rotating, and this one will roll. So we're going to have a frictionless between the shaft and the hole because the bearing is sitting there. That's one of the examples that we have. So you can see that the arrow tells us first what the shaft diameter tolerances is going to have a maximum and minimum value. The manufacturing tolerance of the bearing is going to have minimum and maximum diameter. And we have the housing board tolerances, once again, is going to have minimum and maximum diameters. And we're going to have the minimum initial radial clearance between the shaft and the bearing sleeve. The conceptual design for the speed reducer is going to be introduced as one of the examples we have there. So we're going to have tolerances between the hole of the bearing or the inner sleeve of the bearing and the shaft diameter in all the bearings. And also we're going to have some tolerances between the hole diameter and the shaft diameter that prevent the oil from slipping. We are going to actually add some seals there, and once again we're going to have some tolerances to be done. So here the outside race of the bearing should be actually fit inside the hole directly, so we can remove it and fit it in by hand. But in the case of the shaft inside the bearing, this will be added by using a force. So it's going to have something like the interference, which is going to make it harder to take it off. So we start with tolerance, and we need to define what the tolerance first. So we come to the point that the tolerance is going to be a range between the permissible maximum and minimum limits of the size of the workpiece or distance between the features. So let's have an example on that. So I said that I would like to have a hole that's going to have a shaft that be sitting in and rotate. So that means I'm going to have this diameter of that hole should be something like, the shaft is 25 millimeters, so I should get something like 25 up to 25.1. So it's going to be either fit or it's going to be a little bit larger, because if you're going to have it smaller, they will interference and then they're not going to be able to move. If I'm going to have it more than 25.1, then it's going to be loosey, and this will cause vibration and damage for the shaft. So the tolerancing itself is the technique whereby the tolerance is going to be determined. Some functional dimensioning and the tolerancing we have. These are some of the section drawings for the rotating lever fixed at the machine with the stepped bolt. So you can see that this was going to have multiple levels here, and we can have the surfaces. We're going to be 1, 2, and 3. These are the parts. This is the bolt, this is the body, and this is the lever. Okay, well, I need actually to explain how this one is going to look like. So I'm going to sketch it roughly. I'm sorry, I just passed this one. Anyway, I'm going to try to, where is it? It's here. Okay, so I'll try to make a drawing for this roughly. So this is the wall, and we're going to have the hole. Over the hole, we're going to have a lever that will have the ability to swing forward and backward. Okay, so that's the frame. That's the frame, and that's the lever, and that's the hole. This hole is going to be here, and the hole for the lever is going to be a little bit larger, because we're going to have the screw going to have multiple diameters. So screw is going to be sitting here. So now we're going to have some tolerances that the screw actually is going to be fixed with the body or the frame, but it's going to have some freedom of the tolerances at this stage. So step 1, we're going to determine the intended functions of the assembly. So the lever, let me clean that. So the lever must be able to rotate freely, but without excessive movement in the radial or axial directions with respect to the screw axis. Now, step 2, decide how much clearance is going to be needed. Well, I told you that actually if there's going to be too much clearance, that means that the body will start to have a loose movement, and this will cause damage. So the clearance is going to be needed to allow the free movement without producing an excessive axial movement. So dimensions we have here, like the A, the B, the C in the drawing, should have a free movement. So they're going to be too close to here, but not too much, because too much we're going to have the axial movement. So the lever can move to the left and right, and this is not going to be something desirable. Then the diameter of the hole in the lever and the shaft of the bolt will determine the radial play between the two components. Finally, often these decisions influence the customer perceptions of the build quality. Step 3 is going to be assign the dimensions. So the values for the A and B will reflect the axial play. So we need to take care about those values. Value for the C, which is going to be that tolerance here, okay, is going to be non-zero, so that the thread does not actually bottom out, resulting in more clearance than expected. So we just need to have the thread to be to this point, just at this area. The functional dimensions of the components now is going to be defined like the F, the F, the F, and the F. So we have the maximum and the minimum values between both. That's the maximum, that's the minimum to provide the value for the B. Step 4, we're going to specify the size, the form, orientation, and the positions in the drawings. So we're going to include each of the dimensions directly will clutter your drawing. So use the indirect and the implicit methods of the dimensioning to overcome this problem. So you can do either the direct dimensioning, or you can do the indirect dimensioning, or the use of the notes and the symbols. So first, let's see how we can do the direct and the indirect dimensionings. Before I get to show you the next page, if I get to have something like that, that's a cross section of the shaft. Okay, so if I get to say that this distance is going to be 100 millimeters, and that distance is going to be 60 millimeters, so the total is going to be 160. I did a direct dimensioning. But if I get to say that this one is 100 millimeter, okay, I'll remove this one, and then I'm going to say that from here to here is 160. That means you can find out that this distance here is going to be 60 by indirect dimensioning. Also, we can use some notes and some symbols for that. So the next page is going to show you this example. You can see that these are the direct dimensioning is shown here at the top. We can simply just put the lines and put an arrow between them, dimensioning arrow. And we're going to say, okay, now this is the distance going to be 60. We put plus minus 0.05. That means this distance can be 59.095, and it can be 60.05 millimeter length. We have 40 plus minus 0.05 for this length, and we have 15 plus minus 0.1 for that length. Now we take a look about the chamfers. All the chamfers actually has been mentioned. Here we have the diameter of the section, and we are going to have the tolerance for this diameter. So again, you can see it cannot be smaller than, but it can be cannot be larger than, but it can be smaller than the 29.9. Same thing we can have for the bigger diameter of the shaft here. Now here it's not mentioned what the total length of the shaft. So this will be an indirect dimensioning. So you can simply just add these three values, and you will get the final dimension. So these are the direct and the indirect dimensioning. Here also we can use some notes and samples. So for example, so for diameter here, we'll say that we have 4 holes, 1, 2, 3, 4, and the diameter is going to be 15 with a plus 0.3 and 0 at the bottom. So that's the maximum diameter is 5.3. The minimum diameter is going to be 15. We cannot go smaller than that. So we go back once again to the tolerances. So tolerance refers to the permissible deviation of the dimension from the specified basic size. Okay, so it's how much more or how much less. So we are going to you're going to either have the unilateral tolerance, where the deviation is going to be only in one direction from the basic size. It's either going to be more or less than the basic size, or also we can have the bilateral tolerances, where deviation is going to be in both above and below the basic size. The total tolerance refers to differences between the maximum and the minimum permissible dimension. So the components and their tolerances name are given according to the Australian Standard 1100-101 for the technical drawings general principles for 1992. So the components we have, For the size, we can have the bilateral, the unilateral, and the limits of the size. For the form, we can have the circularity, the cylindricality, the flatness, and the straightness. For the orientation, we can have the angularity, the parallelism, the perpendicularity. For location, the positions, including the consistency and symmetry. And with surface texture, we can have the RA, which is the surface roughness, and the various other measures. For the profile, we can use the line of the surface, and for the run out, you can use the circular or the total. The allowance refers to the intentional difference between the maximum material limits of the mating parts. This can be positive allowance for the hole and shaft pair will define the minimum clearance between the mating parts from the largest shaft mating with the smallest hole. A negative allowance will result in the shaft of being larger than the hole, which is going to have something like the interference. Okay, so now you understand that. If I get to once again sketch that for you, so we're going to have, in the case of the positive allowance, okay, so this will be the hole. Then define that the minimum clearance between the two mating parts from the largest shaft mating with the smallest hole. Okay, so that's mean we're going to have that. Diameter of the shaft is more than the hole. Negative allowance will result in the shaft being larger than the, that's the negative one. We're going to have the interference. Positive one, we're going to have a clearance. So that will be diameter of the shaft is going to be smaller than the diameter of the hole. Okay, so that will be the positive and that will be the negative. So for example, if we're going to have the dimensions to be given as 1.625 plus minus 0.002 means that the manufactured part may be 1.627 or 1.623 or anywhere between these limit dimensions. So the tolerance here is 0.001 or 1 in 1,000 of the inches for the hole as well as for the shaft. You can see here that the minimum and the maximum are given. So the minimum diameter of the hole is going to be 1.25 inches. The maximum is going to be 1.251. For the shaft, it should be the maximum is 1.248 and the minimum is going to be 1.247. So the tolerance here is going to be 0.01 for the hole as well as for the shaft. These are the limit dimension we have. So small tolerances usually going to mean a higher cost as shown in the graph below. So if I would like to have very close tolerances like the one in the 10,000 of the inches, that mean I need to have more precise machining process. Okay, and thus the cost is going to be increasing. So you can see here about the increase in the machining cost on the y-axis and the machining cost we have in the x-axis and the total tolerance we can achieve from that. So you can see as I get to move from the micro inches dimension from the left to the right, okay, you will see that the 4 in micron of the inches is going to be done by the sewer finishing lab process. That's for the lab 8. The honing is 16. Something like, like the finish turning or the semi-finish turning. This can be almost have, whenever we're going to move forward, we're going to have a better service finishing. And thus we're going to have a better tolerances for the parts. You can see that the percentage of the increase we are going to have for the cost is going to be up to 800% if I would like to do the sewer finishing over just the normal machining. That's the rough tolerances and the rough cutting. Something like the flame cut or the forge or the cast cutting is usually going to have the worst tolerances and thus is going to be the least cost. Okay, once again, let me remove the So some of the size designation we are going to have here are going to be first the nominal size. So the nominal size is a designation used for the general identification and is usually going to be expressed in decommon fractions. For example, in the previous figure, the nominal size of both the hole and the shaft, which is 1 inch and a quarter, will be 1.25 inches in the decimal system of dimensioning. For the basic size or the basic dimensions, it is the theoretical size from which the limits of the size are going to be derived by the application of the allowance and the tolerances. The actual size is going to be the measured size of the finished part. The allowance is the minimum clearance space intended between the maximum material conditions of the mating parts. So it's either the allowance is either the minimum clearance space or sometimes going to be maximum interference intended between the maximum material conditions of the mating parts. So these are some of the examples for the allowance and clearance. So you can see here that the shaft is 1.247, minimum 1.248, maximum for the hole is 1.25 inches minimum, 1.251 maximum diameter. So that's mean that the shaft tolerance is going to be the 1.248 minus 1.247, and this will be 1 in thousands of the inches. For the hole tolerance is going to be 1.25, which is the maximum diameter minus the minimum diameter, and this will be once again 1 in 1,000 of the millimeters. Now we are going to go to check the loosest fit, which is going to be the smallest shaft and largest hole. So the largest hole is going to be 1.251, and the minimum diameter shaft is going to be 1.247. And thus I can find the maximum allowance, maximum clearance to be the difference between them, which is going to be here given as 0.004 or 4 in 1,000 of the inches. That's maximum clearance. For the allowance is going to be the largest shaft and the smallest hole. So the largest shaft is going to be 1.248, and the minimum diameter of the hole is going to be 1.25. So the allowance is going to be 0.02. That's mean always going to have a clearance. There will be actually no interference between them. So the basic references for the tolerances and the fits are going to be the Australian Standards AS 1654, which is an ISO system of the limits and fits, and the basis of tolerances, deviation, and fits. The ANSI standard B41 for 1967, preferred limits for the fits and the cylinders, and this was used in the United States. We have the ANSI B42 for 1978, and this is for the preferred metric limits and fits, and this is for the metric system, and this is what the one we're going to use heavily. So the tolerance grade refers to the set of the tolerances that can produce with an approximately equal production capability. So the smaller number means a smaller tolerances. Example is going to be shown in the next slide. So here we're going to have the application and the measuring tool, and the application and the tolerance grade we're going to have. So we start with the measuring tools. Okay, that's for the tolerance grade. Measuring tool is going to have something like 0.1 up to 7. That's the tolerance grade we have for it. If I'm going to go to the rough forms, like the casting, the sewing, and the forging, is going to be between 12 and 16. So you can see how bad actually the tolerance grade we are going to have when the number is going to be higher. The smallest is the best, and that's what we mentioned actually in the previous page. Now we're going to have for the nominal size in millimeters, and the tolerance we're going to have in thousands of the millimeter for different tolerance grades. So for example, I'm going to have the example of the fits of the machine parts, and I'm going to take the 9. So I'm going to come to here to number 9, and I'm going to check about what will be the tolerances in millimeters if I'm going to have, for example, a hole diameter of 20 millimeters. So 20 millimeters will be located in the 18 to 30, okay? And I'm going to check it with the 9, and I'm going to have 15 10.8 divided by 1000 of the millimeter is going to be the tolerance value for this hole. Okay, so that's how we use this table. So for the decimal dimensions, the dimensions in inches, the tolerances are going to be as follows unless the otherwise stated. So it's going to be xx.x, xx.xx, and we can add to thousandths, and we can add to tenth of the thousandths. For the angles, we can write it down as plus minus 0.5 degree. Where the x represents a specified digit we are going to apply. So, for example, I can write it as 10.1. I can write it as 10.15, 10.156, 10.15678, and so on. Okay. Now, another example, if we are going to be given the dimension has a basic size of 2.5 inches, then the dimension can be stated on the drawings in any of the four ways with the different interpretations. Like, for example, 2.5 means it's going to be 2.5 plus minus 0.05, or the limits of the 2.55 maximum and 2.45 inches minimum. 2.50 means it's going to be 2.5 plus minus 0.01, or the limits of 2.51 to 2.490 inches. Once again, whenever we're going to add zeros, that means that the tolerance will be always going to be decrease in value, as you can see here. Okay. Now, the next video is going to be about the second part, which is going to be the geometric dimensioning and the tolerances. Tolerancing, which is going to be the, we can make it as a shortcut as the G, D, and T. So that's what we're going to cover in the second video. So thank you for attention this part. And just remember that most of the information we have here are going to be the one we are going to have in the quiz.